Ladies and gentlemen, the work we are presenting at ICME 21, University of Tamanrasset, is entitled Optical Spectroscopy Study of 4F interbond transitions in crystalline fluoride materials doped with thulium-luminescent ions. It was carried out at the Laser Physics Laboratory of the University of Annaba. The studied matrix is a single crystal of strontium fluoride doped with thulium ions with a molecular concentration of 2%. We have put together in this slide the main characteristics of this host matrix. It has a cubic structure of fluoride type having a cell parameter of 5.8 angstrom. The cell has 4 formula units, that is to say 4 strontium ions and 8 fluorine. The SRF2 compound has a high melting temperature of more than 1450 degrees Celsius. As other characteristics, but advantageous this time, the SRF2 compound has a wide optical transparency range which extend from 130 nanometer to 11,000 nanometer. In addition, its dispersion equation is well known in the literature, and we have the values of the refractive index at any wavelength. This compound is also considered to have very low phonon energies. Therefore, this property gives it a great advantage in emission spectroscopy. It also has a very acceptable thermal conductivity, since it is close to those of materials that gave the laser effect, such as YAG and fluorite CaF2, or almost 10 watt meter per Kelvin. We first studied the SRF2 single crystal by X-ray diffraction. The diffractogram in question mainly shows a single intense diffraction peak identified as being corresponding to the diffraction on the reticular planes 200. This reflects the fact that this direction is favored during crystal growth. As the first optical measurement made on the studied sample is that we recorded an absorption spectrum which was calibrated in emission cross-section over the UV visible and near-infrared wavelength range. In the first part of the spectrum, that is to say, in the UV visible part, the recorded spectrum is well structured and is formed of very distinct sharp lines. On the contrary, in the infrared part, there are 2 bands almost 400 nanometer wide in the extreme part of the spectrum. Since thulium ions can emit in the blue around 450 nanometer, we have to record an excitation spectrum to get the correct excitation wavelength. This spectrum shows mainly two excitation wavelengths. Using either wavelength, we get a Stokes emission spectrum formed mostly of emissions from the 1D2 level, one in UV and the second in blue around 450 nanometer, associated with the transition between excited level of thulium ions. This allowed us to draw the diagram of the main Stokes emission of thulium ions under each of the excitation wavelengths. The blue emission at 480 nanometer is only obtained by upconversion under infrared excitation around 770 nanometer. This phenomenon is interpreted by the successive absorption of two photons which inhabit the 1G4 level, de-energizing directly in the fundamental level. We are also able to record the infrared emission around 1.8 micrometer, which is known to have many practical uses. The emission is reinforced by a phenomenon of cross-relaxation very effective in view of its intensity. In conclusion, the SRF2 crystal doped with thulium ions exhibits two important emissions, one in the blue around 450 nanometer and the other around 480 nanometer. The other in the infrared around 1.8 micrometer. These two emissions exhibit important fluorescence characteristics, that is to say, high emission intensities, strong branching ratios, and metastable lifetimes. The laser emission possibilities both in the visible and the near infrared range. Thank you very much for your attention.